Evening, everybody. 5 o'clock Thursday night. Time for some Calc 3. Last section in 14. So there'll be a module quiz in the somewhat near future. So make sure you know when that is due by. You can always do it early. But just a reminder. And then we'll be starting our last module of the semester next Tuesday. So what I want to do for today, I want to talk a little bit about the Jacobian, do a couple of examples, one maybe a little easier, one maybe a little bit more difficult, and then see where we're at, see what kind of questions come up out of doing those examples for this section. And then if we do have time at the end for groups, we will, and we'll probably actually work on 14.7, because I think that's a little bit more important section for what we're doing now and what we'll do the rest of the semester. Because in a way, we already know how to change variables. Now, we've done it in a couple of specific cases, cylindrical and spherical. This is more general. So this is how you would change variables in general. Those cylindrical and spherical are two specific cases. All right, so that's really what this section is about. It is worth seeing the Jacobian. For those of you who are in linear algebra or will be taking linear algebra, you'll see the Jacobian again. It basically accounts for the amount of rotation as you change systems. So the Jacobians are very useful when you're working with matrices. All right, so I want to dive into this section. Like I said, I'm not going to spend a lot of time on the concept, but I do want to do a couple of examples. And guys, I think you're going to find this is one of our easier, shorter sections, especially like there's not a lot of homework questions on it, because again, you're changing variables when you change into polar, or when you change into cylindrical, or when you change into spherical. So you're already getting practice with that. This again is more general. We'll talk about why we care, and look at a couple of examples. All right, so basically, same idea as when we introduced polar, cylindrical, and spherical. Sometimes these other systems, or sometimes making these transformations, makes the integral easier to do. And that could mean one of two things. It could make the limits on our integral, or region that we're integrating over, easier, or it could make our integrand easier, or both. Ideally, both. We want to make things less complicated. So this is just an example. I'm not going to spend a lot of time on this one, but basically here's what's happening. So our region R is the region in the XY plane that we want to integrate over. And we can see, it's really tough to tell. The bottom is different here than it is here. The bottom here is different than it is here. Well, by using this transformation, we actually move it to S, which is a rectangle in the UV plane. And as we've discussed in the past, rectangles are our favorite region to integrate over because all the limits are constants and the order doesn't matter. Okay. So this is going back and forth between the two regions. Now, again, we get the same integral. What we're doing is a mapping from R onto S, or S onto R, depending on what direction we want to go into. And by making that transformation, we make our integral easier. As an analogy, think about what we do when we have a circular region in the XY plane, right? When we have a circular region in the XY plane, well, that's can be messy to do in rectangular and won't be all constants, right? We've looked at that before, but in cylindrical or polar, depending on if we're 2D or 3D, doing a circle for our region is all constants. Hence why we change from rectangular to polar. Same idea here. All right. Now, computing the Jacobian, this is going to be purely procedural. This is where, as always, guys, use your note cards, because I will ask you to compute a Jacobian on the final exam. It won't be a terrible one. I'll talk a little bit more about that as we go through them. But, I don't want you to try and memorize how to calculate a Jacobian. I just want you to be able to calculate a Jacobian and understand what it's used for. That R that we have to add into our integrand and polar, as you saw, it comes from the Jacobian, and the rho squared sine phi that we have to add in spherical comes from the Jacobian. And they're both calculating the determinant of a matrix, 2 by 2 for a 2D. The examples we do today are going to be 2D. Most, if not all, the ones we do in this class are going to be 2D. If we're doing it in 3 dimensions, then it's a 3 by 3 matrix. And you saw that in the video lessons, a 3 by 3 matrix was used to calculate the Jacobian for spherical. So what the Jacobian does is it talks about how to it basically accounts for transforming the region. So in that previous example, to turn R into S, we have to move and you can see how the sides correspond. The red corresponds to the red, the green to the green, blue to the blue, black to the black. What the Jacobian does is it accounts for taking R and straightening it up and flattening out this side. The Jacobian takes care of all of that for us, which is actually really cool if you think about it, and allows us to make our region something that's easier to deal with. Calculating it is no more than, we're just going to talk about the 2D Jacobian first. Like I said, both examples I'm going to do today will be 2D. We'll talk a little bit about the 3D, but I'm not going to have you do any 3-dimensional Jacobians in here. So I don't want you to get too worried about that. Definitely not on the final. They just take too long. So we do the 2D Jacobian, and we do basically what's called the determinant of a 2 by 2 matrix made up of the partials. dx du, dx dv, dy du, dy dv give us our 4 terms. And then I always and this goes back to when I was learning to do determinant of a 2 by 2 matrix, I basically think it kind of looks like a fish. And let me show you what I mean by that. I know that might sound kind of weird at first, what looks like a fish. So I think of a kind of a fish shape when I'm doing 2 by 2 matrices, meaning I do this one times this one, and this one time minus this one times this one. And there's my little fishy. And guys, that's how I memorized how to do a determinant of a 2 by 2 matrix. So it's not hard to do, again, procedurally, and we'll do a couple in the examples. But again, depending on, everybody here is heading into different areas. Some of you guys may be using Jacobians a lot, especially if you do things that involve morphing objects. What I mean by that, if you can think of when you see on a video of one object morphing transitioning into another object, that is done with these Jacobians, with these rotational matrices, a whole bunch of them. And what they do is they actually take it through the process of the beginning image to the ending image. So we're just really scratching the surface of this stuff, but very useful, useful items. So now this would be if our substitution is for X and Y in terms of U and V. I'm actually not familiar with the kid animal morphing books. The one that I always think of, granted, this is really, really old. There was a the Michael Jackson video, black or white, where the face of the people dancing. Yeah, you guys probably know what Cooper's talking about, but I'm not sure. But if you guys remember, I don't know, I'm totally dating myself now, but there was a Michael Jackson video for black or white back in the early 90s where at the end, and this was cutting to edge, thanks, Andre, that was faces morphing, into other people's faces. That's basically what these Jacobians do. Now, obviously, they're more complicated than the ones we're looking at here, but that's the idea behind them. And that's what that means when it's saying these are the Jacobian counts for the amount of rotation or straightening or whatever's going on in our transformation. Depending on which way we're doing our transformation, the Jacobian can also go in the other direction. Most of ours are going to be changing XY into UV, but I just want you to be aware of this. But let's do an example. Let's make this a little bit more concrete, okay? So what happens is we have some function in terms of X and Y, and then we make that function be in terms of U and V, and then we include our Jacobian and then du dv. Again, as we've seen, this is exactly what happens when we change to polar, right? The x of uv would be our transformation for x, which is r cosine theta, our transformation for y, which is r sine theta, and our Jacobian, which we know is r. So we've actually already done this just in a very specific case. So basically now we're looking at the more general case. So let's look at this example here. So here's our transformation, x equals u, y equals u plus v. Now the regions on this one aren't terrible, but this is not pretty. So this is one where we might use a transformation to make our integrand a little bit easier. Well, let's talk about how we would do that. Now, x equals u and y equals u plus v, those actually just sub right in. So we can actually already start with that. Oops. So this will be our integral where we want to end up. So what we do is we replace x with u. So this becomes u times u plus v minus u squared. All right, and then we'll put our Jacobian up here, and we'll talk about our order of integration as we change that over. So let's do our Jacobian next, and then we'll do the limits. So our Jacobian, this time I'll write it out, and the next one I might not. So dx du, dx dv, dy du, dy dv. And as always, guys, remember, this is not something I'm expecting you to memorize. This is something you can use your note cards for. That's what they're there. That is exactly what they're for. All right, so we really just go to our transformation. So the derivative of u with respect to u is 1. And then x with respect to v, well, there's no v in it, so it's 0. And derivative of y with respect to u is 1. And derivative of y, which is the u plus v, is 1. So there's the values for our matrix. And now we take its determinant. Remember, I kind of call it the fish. So it'll be 1 times 1 minus 0 times 1. 1 times 1 minus 0 times 1. We get a very easy Jacobian of just 1. So 1, and then we will have to come up with an order, but let's see what our limits are first. Before I go any further, any questions about where the values for my matrix came from? The 1, 1, the 1, 0, 1, 1?
Yeah. Yeah, where'd you get them?
So remember, so remember what this means, right? This means we're taking the derivative of x with respect to u, and we know that x equals u. So the derivative of this with respect to u is 1 because we're taking the derivative of u.
Got it.
And the other one, y equals u plus v. And that's why we got 0 when we took it with respect to v, because there is no v in it. And then this one, like I said, this is kind of an easy one. We'll do another one where I think it'll be a little more interesting on the Jacobian. Here, when we're doing, dy du, it's just 1. Dy dv equals 1.
Oh, okay. So just take it like a partial.
You got it. We're taking partials. Yep. Good. I'm glad you asked. That's important, guys. We need to know where this stuff is coming from. All right. So we got that part down. The Jacobian, we're good. That's in. Last thing we really need to do are the limits. Now, we know that y equals u plus v, and we also know that u equals x, okay? Right here. So I'm going to plug the x in here. So we got y equals x plus v. Well, notice here, these limits were y values. So v has to go from, so y, y, let me write this out so it makes it real clear. Y was in between x plus 2 and x plus 3. Well, if y is x plus v, then v just needs to be in between 2 and 3. Because that's our transformation. So those are going to be our limits on v. Now, x actually ends up being real easy on this one because u is just x, and x we know is from over here. These are our limits on x. X was between 1 and 2, and u was equal to x, so u has to be between 1 and 2. So what this tells us is, as far as the limits go, the order doesn't matter because our region is rectangular. So the only thing that might make a difference in our order is what our integrand looks like. But it turns out if you simplify this, so we distribute the u here, we end up with u squared. Let's write it out, actually. Of course, I ran out of room. Let's make a little bit of space here. All right. So the limits for v the limits will come from are born out of the transformation. There's a couple different ways, and I'm going to show you another way in the next example. But the way we got the limits for v, remember that we use the transformations, which is that y is u plus v, but since u is x, we can actually say, okay, well then y equals x plus v. Now, separate as its own x plus v. Now we know that y has to be in between x plus 2 and x plus 3. Well, because of our transformation, that means v is just going to go from 2 to 3. Because y is going from x plus 2 to x plus 3. V is just going to go from 2 to 3 to make x plus 2 and x plus 3. Questions about that? So if we distribute this u, we get u squared plus uv minus u squared. So those actually end up canceling. And we're going to go back and fill in everything else here on those. So really, this actually simplifies all the way down to 1 over square root of uv, which actually the order is not going to matter. Now, this may not look like the prettiest integral as written, but remember, this can be split into 1 over square root of u times 1 over square root of v, and then we do each of those separately. The order doesn't matter, so we could do dv first and then du. Let's just we'll put dA since we didn't decide until the end. So if we do dv, v goes from 2 to 3, u is going to go from 1 to 2. And this is actually not a bad integral. Again, just we're not going to solve this one just because of time's sake. But remember, we could rewrite this as u to the minus 1/2 times v to the minus 1/2. And then just do each of those separately. Those are actually basic antiderivatives. So a significantly easier integral than we started with. So this is a good example of one where we use this transformation. It makes the region easier because we go from a parallelogram to a rectangle. But it also makes the integrand significantly easier. Questions about this example? All right, let's do one more. And this one is going to be from the worksheet. Like I said, I want to do one that was a little bit tougher, so you guys can see a little bit more what's going on with these. We're going to do number 4. It's actually probably the toughest one on the worksheet. So number 4 here at the bottom. All right, so we've got this double integral here. Let's see. All right, we've got a double integral here over a region R. Square root of y over x plus square root of xy dA. The region is bound by y equals 1 over x, y equals 4 over x, y equals x, y equals 4x, and they give us the substitutions to use. So x equals u over v and y equals uv. And the ones that we're going to be doing in this class, you will be given the substitutions. I don't want you to worry about finding them. There's something that's a little bit outside the scope of what we're doing in here. But you will see how you will see once we go through these how they relate to the functions. It's actually pretty cool. All right, so what I want to do is I want to bring up our region so we can take a look at it. I have it here. All right, don't want to cover up the problem. This is our region right here. Might not be terrible to do in rectangular, but it's not going to be pretty. Our goal is to get it onto a rectangular region so that all our limits are constants, especially because of these radicals. There's a lot of things that can go wrong. Now, let's talk about going through this guy. We have a couple things that we have to do to get to our final answer. So let's kind of follow the same procedure. First thing we have to do is we're going to sub in these, but also do the Jacobian. So let's do our Jacobian. And so remember how it went: dx du, dx dv, dy du, dy dv. Okay. So we're taking the derivative of x with respect to u, which that's just going to be 1. Remember, v is a constant. These are partial derivatives. So 1 over v. And then dx dv, that's the derivative of u times 1 over v, or, we might want to write it as uv to the minus 1, right? So we drop the negative down and decrease the power by 1. So this becomes negative u over v squared. Remember, all these terms of the Jacobian are just partial derivatives of our substitution. Now we do here's going to be the derivative of y with respect to u, which just leaves v. And then the derivative of y with respect to v, which just leaves u. All right. Now, before I go on, questions about where any of our terms of our matrix came from? I was just following the same pattern as last time. I just didn't write down the formulas this time. Okay, determinant time. So we do the little, what I call the fish thing. So this guy times this guy. So 1 over v times u. Let's see if we can make that a little cleaner. One over v times u minus now the other half of the fish, minus uv squared times v. Okay. So what do we get? Over here we get u over v minus a negative, so it's going to be plus. And we can essentially cancel this v out with one of our v's down here. So plus u over v. So we get 2 u over v. If you want to write the 2 out front, totally fine, because we got 2 of them. That is our Jacobian. We have to make sure we put that in as part of our dA. All right. Questions about the Jacobian calculation? All right, we're getting there. Next thing we do, let's substitute everything in and see what happens. We'll do the limits last. Okay, so y is uv, x is u over v. So we have, you'd think by this point in the semester, my writing on these things would get better, but it has not. uv over, and then x is u over v, plus square root of x, which is u over v, times y, which is uv. We put in our Jacobian, which is 2u over v, and we haven't decided on an order yet. All right. So here's what we've done so far. We have found the Jacobian. We have substituted in our transformation. We're going to clean this up, do as much simplifying as we can here in a second. And we put our Jacobian in. So next step would be to clean this up and then figure out our limits. So let's go ahead and clean this up first, and then we'll do our limits. So under the radical, remember, if you divide by a fraction, you flip it and multiply. So this essentially becomes UV times V over U. Plus, now this, the V's will cancel, and we end up with the square root of U squared, which will simplify, which is U. We'll do it in the next step. 2U over V. And then we have to pick an order once we know our limits. Something real similar that happened here is going to happen here. And here we're going to end up with square root of V squared. So after all is said and done, this becomes square root of V squared, which is V. And we got square root of U squared, which is U. And then 2U over V dA. Now, before we go to integrate, we'll want to distribute this, but let's go ahead and talk about finding our limits, because that's really the last key to this and is a little tricky the first time you do it. But pause there. Any questions at this point? Okay. Here's what I'm going to do, guys. I'm going to go, because I want a little more space to do this part. I'm going to start a new whiteboard, and then we'll come back once we know the limits. So actually, I'll put a note here for when you see it later. So limits on next whiteboard. All right. Let's give ourselves some space. All right, here's what we need to do. And I lost my graph. Sorry about that. Notice I already put on the intersection points ahead of time. Okay. And guys, remember, we've done intersection points before. To find intersection points, you set the two equations equal to each other. Find your X and then sub back to find your Y. So that's how we would do it algebraically. For time's sake, I didn't want to do that. But these corners of our region will be the corners of the region in the UV plane. Okay. So this is pretty cool. And I think this one, the reason I like this example is because it can really, I think it does a good job of showing how these transformations work. So what we need to do is map these XY points into UV points. Okay, we have our two transformations. So what I'm going to do is I'm going to change the points first, but then I'm going to show you what's actually going on. X equals U over V. Y equals UV. All right, so our first XY point, we can do any of them. Let's go ahead and do 1/2, 2. All right, let's talk about changing that point. So if I have the point X equals 1/2, Y equals 2, basically you just put those in for X and Y here. So 1/2 equals U over V, and 2 equals UV, because now we have a system we can solve for U and V. So we might cross multiply here, right? So multiply the 2 up there and the V up there. So we get that V equals 2U. Sorry for my handwriting. This is a 2, not a 1. And then we can sub that in right there. So we get 2 equals U times 2U, or 2U squared. So if 2 equals 2U squared, we can divide both sides by 2, take the square root, and we're going to get U equals 1. Now it's true, in solving, we would get, algebraically, we would get U equals +1 and -1. but since we're in the first quadrant in the XY plane, we'll be in the first quadrant in the UV plane. Now, if U is 1, we can get V because V is 2 times U. So that tells us that V equals 2. So this is going to transform into the point 1, 2. All right. We're going to do this for all 4 points, and then I'm going to come back and show you something afterwards. So you'll get the hang of it real quick because we're going to do it 4 times over. We got the point 1, 4 here in the XY plane, and we want to transform that into a UV point. So we have 1 equals U over V, and 4 equals UV. Solving this one, I think, is the easiest one to solve because you cross multiply the V, you get V equals U. You can plug either one you want into here. So if we plug V in, we get 4 equals V times V. Oops, I lost my equal sign. Sorry, guys. A little too quick. So 4 equals V times V, or V squared. So 4 equals V squared. That's going to give us V equals 2. And if U and V are equal, U is also going to be 2. All right. Nothing crazy going on here. I am literally just taking the points of intersection. Let's do 2, 2 next. Change it to a UV point. I'm just plugging them in for X and Y into our substitution. So I get 2 equals U over V. And I get 2 equals UV. So here we end up with 2V equals U. Plug that in here. What ends up happening is you get 2 equals 2V squared. That's going to give you V equals 1. And since 2V is U, U equals 2. All right. And so that would transform into the point 2, 1. And guys, if you have questions as I'm going through these, please let me know. But I'm because I know I'm going through them a little bit quicker as I go through more of them because I just don't want to bore you. But all I'm doing is I'm saying, okay, I've got the point 1, 1 in the XY plane. I want to transform that to UV, so I'm just going to put it into my substitution. So 1 equals U over V, 1 equals UV. So again, U equals V. You substitute either of those in there, you end up with, U squared equals 1. So U equals 1 and U and V are the same. So 1 again. Sorry, that should have been a V equals 1. All right. So these are the points in the UV plane. Now, here is the part that I want to show you. Like, this is a rectangle. 1, 2 to 2, 2 to 2, 1 to 1, 1. That's just actually, it's a square. U's going from 1 to 2, and V is going from 1 to 2. Yes. What we're finding now are the bounds on U and V. And what we're finding is U is in between 1 and 2. And V is in between 1 and 2. Because U goes from 1 to 2 as V, while V is 2. So basically, our region in the UV plane is this square right here that goes from 1 to 2 in the U direction and 1 to 2 in the V direction. Yep. So we've got our limits, guys. There's just something I want to show you before we go back to the integral, because I think it's important to see why this works. And I think it's actually kind of cool. So what I want to do this. I am going to bring over another whiteboard to do this because I want to leave up what we have. So this, let's see. I'll get this situated so we can see everything. I do want to keep our graph up too. Getting a little crowded, but I'll figure it out. All right, so all we really need are these points. Okay, so this is actually really neat. And this is kind of the key here. All right, I like that. So if u equals 1, right? So now we're talking about the case where u is equal to 1. Look at what happens. Then from our transformations, x equals 1 over v and y equals 1 times v, right? We're letting u equal 1. Now, because x equals 1 over v, we can solve this for v, right? Multiply the v, divide by the x. Well, that's the same thing as v equals 1 over x. And plugging that in here, we get y equals 1 over x. That was our green curve. Okay, so when u is 1, it's representing this boundary right here. Now, if u equals 2, let's see what happens. We get x equals 2 over v and y equals 2v. And now again, we'll solve this for v so we can plug it in over here. Well, v equals 2 over x. So plugging that in there, we get, I want to write it all out, y equals 2 times 2 over x or 4 over x. Remember, that was this boundary. This went from 1 over x to 4 over x. So when u goes from 1 to 2, we're going from the boundary 1 over x to 4 over x. So what would have not been possible in rectangular, because we can't go from this green to this blue, is now possible with this transformation. Again, now this is not something I'm expecting you guys to do. The reason I'm doing what I'm doing right now is I want you to see how these transformations over here, how u going from 1 to 2 is the same as going from y equals 1 over x to y equals 4 over x. If you got something like number 4, you would need to graph it because you would need those intersection points. And then you would use then you would just use your transformations to transform the points like we did over here. So what you will be given is the transformations. If you get something like this, you can graph it and find the intersection points. Like I said, basically all you do is transform the intersection points, because the whole point of these transformations is to get on a region so that all our limits are constants. Real quick, I want to do the same thing with v just so you guys can see it. So let's make that a little smaller. I won't spend a lot of, so if v equals 1, let's see what happens. Our transformations right here. If v equals 1, then x just equals u and y equals u. So this is kind of an easy one, right? Y equals x. So that would be this red curve here. That was the graph of y equals x. So when v equals 1, it's representing this boundary right here. And if v equals 2, then we have, let's go back to our formulas. X equals u over 2 and y equals 2u. So we'll solve this for u so we can plug in, cross multiply that 2, right? We get u equals 2x, take that guy, plug it in there. And that gives us y equals 4x, which is this purple curve. All right. So again, going from v equals 1 to v equals 2 is the same as going from y equals x to y equals 4x. So it turns out our limits are all constants, and we can do this integral in whichever order we find easiest. So going back and putting in our limits, back to this guy.
I got a quick question for you.
Yeah, sorry.
So for every single one of these, do we have to do the when u equals and then one of the points of u, and if v equals? So do this right side every time, or is there a shortcut, or are you just showing us how you're going to get the limits, or do we have to do this every time to get the limits?
So you're talking about what I wrote here in the blue and red?
Yeah.
You'll never have to do that part.
Okay, you just explain to us why.
Yeah,
they work and they're equivalent.
Yeah, I'm just trying, it's kind of like I'm trying to convince you that what we have is representing, what we have in the UV plane represents what we had in the XY plane.
Okay, I got you.
We could have done this whole problem without ever doing this.
Mm-hmm. So once we got the points earlier, we were all good.
You got it.
Okay.
Yep.
All right. Thank you.
Yeah, no problem.
This is just becoming a really long problem, and I was thinking about the homework.
Well, so if this makes you feel any better, I think there's only like 4 or 5 problems in the homework, and I would say that none of them are harder than this one. There might be one that's as hard, but I think you're going to find the homework not bad for this section.
Yeah, I got you. I kind of thought that this part you're doing on the right was kind of redundant.
It is.
And I was just wondering if it's something that we had to do in order to solve it, but I'm glad it's not. Thank you for clearing that up.
No, I'm actually glad that you found it redundant, because it was actually, in a way, it's actually intended to be, right? I'm just reinforcing what we're doing. So I'm actually glad to hear that you found it redundant. So we got limits 1 to 2 and 1 to 2. So the order doesn't matter. So what we would do next, we'd multiply this through. And since they're the same, we won't pick an order just yet till we see what it looks like. So that first part's going to be v times 2u over v, and then plus u times 2u over v. Just call it dA for right now. We got a cancellation we can do there, so that actually becomes pretty easy. And over here, we can't cancel, but we do have a u times a u. So 2u plus 2u squared over v. And gosh, we could really pick the order. Actually doesn't matter, because we could do this one piece by piece. It's not too bad of an integral. So let's just arbitrarily, we'll do du dv. We'll go alphabetical order. I'm not going to work this one out today. We've worked out plenty, and you guys have worked out plenty of double integrals. But if you want to try this one from here for a little bit of practice, the answer is in the answer key on the worksheet. It comes out to 3 plus 14 thirds ln of 2. The ln is going to come in because you're going to be doing an antiderivative of 1 over v when you integrate with respect to v. Oh, yeah.
I have one more question for you.
Yeah.
So can you go back to the graph of this?
Mm-hmm.
Thank you.
This one here?
Yeah.
Yeah.
So I kind of remember, maybe it's only when there's 3 lines that aren't enclose it, but for some reason I remember only the x and y's can be constants and the other ones have to be have to be equations. But in this case, are we making our, so where are our limits at? So is it just between the dot, both the points on the red line? Is that what we're doing?
Okay, so what's happening is, and this is kind of what this is trying to reinforce. What we did when we did this transformation, and basically what this Jacobian accounts for is it takes this region here, this, I don't know, kind of diamond shaped region.
Yeah.
And did I draw it on it? And basically turns it into the region. I don't really have it. Oh yeah, right here. Okay. Basically turned it into this region.
All right. Okay. That's why, because I was wondering because the points didn't match up. But so this is the old, that graph is the old points based on the XY.
Yes.
Plane. Okay. So our new points are the 1 1 2 1 1 2 2 2 2 or whatever.
Yes. And these just happen to be, we have 1s and 2s over here, and we
it's kind of, I was trying to like connect dots that just weren't even there, but they just kind of worked out that there was a 1 1 and a 2 2.
It worked. Okay, it just happened to work out that way.
Depending, that makes a lot more sense.
Yeah, no, it's a good question. Depending on what your transformations are, these points could look completely different than your XY points.
Yeah, but I got to look at my points and go, okay, it's going to go from the lowest X coordinate to the highest X coordinate, and same with the Y, right?
Yeah, because what's going to happen, what happens with these morphings, as you can probably imagine, let's see, so the point 1/2 2 got mapped to the point 1 2 over on this guy. I'm going to try and do this without making too big a mess. So this point got mapped over to the point 1 2 right here. So if it's a corner point on the region R, it's going to be a corner point on the region S.
Okay.
So we basically 1 by 1 took these points.
Yeah, put them over there.
Yep. And so
my question is, when you're trying to determine your limits, I guess my question has actually changed, but it's when you're trying to determine your limits, you don't need to, I mean, I guess it'd be easy to, but would you need to draw out that rectangle and visually look at that? Or can you just look at your points and go, okay, 1 is my smallest X component and 2 is my largest. So I can just make my limits for X 1 to 2.
You mean for U and V?
Yes. Yeah. I'm sorry. Yeah. U and V. So you could just look at the points and know what your lowest U, highest U, lowest V, highest V are, and then determine the limits from there? Or do you think that we should always draw out the rectangle, look at it, and go, okay, X goes from 1 to 2. I'm sorry, U.
Yeah, no, it's a good question. So for what we're doing in here, in Calc 3, in the scope of this class, my answer would be you'll know that they're going to be constants because of our transformations.
Yeah.
Now, obviously, as you get into more complex regions, it is possible that the region that you map to is not rectangular, but is still easier than the region you started with.
Okay.
It's possible.
All right. And it could be an equation as well, so then we'd have to actually write them out.
It could be, yes.
Okay. All right. So for our all intents and purposes, we'll be okay.
Yes.
To look at the points, but
right. For what we're looking at, we're specifically looking at cases where, hey, how can we get this region so it's rectangular?
Okay.
So a good analogy would be, when we were mapping over to a circle in polar, all the limits became constants and it was great.
Yeah.
But when we were doing some triple integrals on Tuesday, if you remember, I still had some cases where some of my limits had to be in terms of a variable.
Yeah.
Because they were messy in that system. What helps? So what helps and what makes this one work? And this is something I didn't really stress too much. What makes this work to go into a rectangle is that this curve here, the green one, was 1 over X. and this was 4 over x. So they were very similar functions. They were the same family, basically.
Yeah.
And these were both linear.
Oh, okay.
You know, and I don't remember what the ones in the homework exactly look like, but if you look at the ones in the, if you ever go and look at the textbook that's in more, you know, two of the lines might be parabolas and the other ones might be they might be linear, or you might have it in, you know, all 4 are parabolas. So what makes this work out so nice is that the opposite sides are the same family of function. Because if we look at our transformations, notice that x is u over v. Well, this was 1 over, sorry, this one was 1 over x. This was 4 over x.
Oh, okay.
Right? Not a coincidence. These were linear. This was 1 times x. This was 4 times x. And this one is uv. So a very linear function there. So that's what allows it to work. And that's where our focus is on this semester. Obviously, like I said, as you go on, regions can have all different sorts of boundaries, and it is possible that the region you map to may not be a rectangle.
Okay. Well, thank you for that explanation.
Oh yeah, no problem. It's a good question.
All right.
And since we were talking about it, one other thing, you know, what happened was we mapped these 2 points to those 2 points. So really what's happening is this edge right here is this edge here of our rectangle, and so on and so forth. We could keep doing that with all the other points, but that's what's happening. That's what the Jacobian does. It accounts for turning this shape into this shape. Other questions at this point? Like I said, I did this one intentionally because I think it's actually going to be tougher than any of the ones you see in the homework. But I also wanted to really bring home that connection of what's happening. Oops, sorry. Of what's happening. And that's why I did this part. This is not something you guys will normally do. You would do this part here. You'd transform your points and say, oh, U's between 1 and 2, V's between 1 and 2. Those are my limits. Okay. Any questions at this point? Still trying to bring home which connection, Andre?
No, I meant like in generic. I'm just still trying to like take it in. Sorry.
Yeah, no problem. It's a lot. The Jacobian. So one thing I can't stress enough: don't get too nervous about the Jacobian, because it is actually really easy to calculate. And while this, you know, this number 4 may have looked difficult, once you guys have done a couple of these, you'll be able to do something like number 4. I'm not even concerned about it. Remember, you're just seeing it for the first time today. But as far as what we're doing in here, this is what we're looking at, how we use the Jacobian to to transform our integral into another variable system. And again, most of the time, we're just going to be transforming into cylindrical and spherical, and we already know the Jacobians for those. In fact, that's the only other thing I was going to mention from this section. You know, you saw this in the video. You do the Jacobian, you get R. That's where that R comes from. And then we do have the 3D Jacobian. You've seen it for spherical. We're not going to do any 3D transformations. We're going to keep them all 2D for Jacobian. So I don't want you to worry too much about this one. All right. Okay. So the question came up, what would what would an exam look like? It would probably likely be just calculate a Jacobian. You're going to see, or not like number 4. On an exam, you would not get anything harder than this. And even this one might be a little bit long for an exam. So more likely it's just going to be to calculate a Jacobian. It'll be reasonable though. It's from a time perspective. Other questions? Okay, we got some time left. Here's what I want to do. Like I said, I'm not actually worried about this section as much. I want to actually, since we didn't have time to go into groups on Tuesday, I wanted to give you a little bit of time to try one of the ones from the 14.7 worksheet. I've just put the worksheet into chat. I'll break you into groups here in a second. I only want you to try number 1. If you get it done quickly, go ahead and try number 4 or one of the other ones. But I want you guys to get a chance to try number 1. You do not have to do it in all the systems like I did. What I want you to do is decide which system is easiest, set it up, and then just calculate it using technology. I want you focused on the setup, not actually calculating, okay? So let me break you into groups real quick. Just so you guys can, I just want to give you guys a chance to try one. Sorry, give me just a sec. Okay, so you got the worksheet. Just try number 1. The goal is just to get you through number 1, set it up, throw it in technology. And remember, look at the fundamental surfaces. If you don't have a sphere or a cone, you don't want to use spherical. If you do, then you do. So if if your surfaces are cylindrical, you might want to try, if you have a cylinder, you might want to try cylindrical. So, all right, I'm going to open up the rooms. You guys try number 1. That'll be the one that you post in chat is number 1. If you guys want, you obviously don't have to. You should have an invitation into the breakout rooms. But I want you to try number 1, just so you guys can have tried one and see if any questions come out of that.